Hi. Now that we discussed about variational inference, let's move on to variational autoencoders. So, variational autoencoders is simply a manifestation of the variational inference and the evidence lower bound objective with neural networks. So, for clarity, I'm writing here the evidence lower bound, and as we see, it comprises two terms here. The expectation term and the KL divergence term. Now, the KL divergence term contains the approximate posterior, and our approximate posterior is a neural network, specifically our encoder neural network. The encoder neural network receives as input an image and returns as output latent code, latent variable z, which is a random variable and therefore a distribution. Our first term is the expectation of the logarithm of a conditional likelihood given the latent variable z, and again this conditional is another neural network, specifically it's our decoder neural network, which receives as input our latent variables and returns as output the input itself. In the standard case, we can have approximate posteriors that are Gaussians, that is our encoder neural network returns Gaussian random variables as z. Focusing on the encoder, or often called inference network, it is our approximate posterior and it can take the form of any standard neural network. We can think of the layers again as feature extractions, which are deterministically determined, right? So these deterministic layers do not play a role into our integral computations, and of course having better layers, better deterministic features might improve in general our computations for our evidence lower bound. In the end, our only goal is with the encoder network is to compute an approximate posterior which is as close as possible to the true posterior, and our network has a stochastic output in the sense that given input x, our output is going to be a distribution over z, not single values. The KL term between the approximate posterior and the prior makes sure that our approximate posterior is not too far away from our prior. Therefore, then the prior acts as a regularizer, as we'll see next. In the case of Gaussian approximate posteriors, it means that we require two neural networks. One neural network for the mean of my Gaussian random variable for z, and one for the standard deviation. So these are two different neural network encodings, the mu and sigma, and the neural networks that we use to compute these encodings, so the parameters of our Gaussian distributions can be sharing the architecture, right? So we can have the same neural network for up to before the output, and have then two different outputs, one for my mean and one for my sigma. The decoder network is also the generative model. It's known as the generative model, and the decoder model is again a neural network which receives as input the stochastic variable z and returns as output a generation, so my variable x. The output again can be modeled as a distribution, and of course we have to make sure that our output distribution matches the type of our data. So if our data is continuous, we have to pick a distribution which returns continuous values as outputs, like a Gaussian or something else. If we have, however, other types of values for our data, like binary values, we should consider different types of distribution, like Bernoulli distributions. With generative models, it's often convenient to think of the generation process. I mean, that's why we call them generative models. So in that case, we start from our generation, like our prior variable z, which can be our unit Gaussian, and then given this z, we can generate every other variable afterward. In that case, the encoder has to be separately, it's not part of this graphical model, but is the variational approximation to make sure that we can address interactability in this graphical model. The prior distribution acts as a regularizer if we take the form of the elbow that we described in the beginning of the sub-lecture. So it makes sure that our approximate posterior does not deviate too much from the prior, and the prior distribution is a way we can induce our own inductive bias regarding our task at hand. Often the prior is simply a unit Gaussian, right? And this is good because a unit Gaussian is easy to sample from, and it's comfortable to make derivations with. If we expect, however, different types of if our data is probably not likely to be generated by Gaussian latent factors, then we might as well pick a different type of distribution. Perhaps we want to have latent factors, latent variables that are sparse in general, so Gaussians are not sparse, like we're always going to give you a number, continuous value number. Or maybe we want latent variables that are binary, 0 and 1. Again, Gaussians will not do that. In that case, we should pick a different prior, and then we should have a sampling process where we can sample from that prior. The KL term will then encourage the approximate posterior to resemble that prior. Of course, variational autoencoders are neural networks, and therefore we have to optimize them. We have to learn good parameters. For the encoder, the good parameters mean that the approximate posterior tries to be as close as possible to the true posterior. And for the decoder, the parameters push the generative model to generate data that produce high likelihoods. Since the two neural networks are having inputs and outputs that are stochastic, the parameters, or at least some of the parameters for our approximate, my approximate posterior for my generative model will correspond to parameters of distribution, not of parameters of a neural network. And we fit good parameters for theta and phi for the encoder and the decoder respectively, with having the following objectives in mind. So we want to make sure that we have good distributions for the latent z for any input x, right? So it means that our approximate posterior should not work only for the inputs x that it has seen during training, but every other x. We want to make sure that our approximate posterior is not too far from the prior. This is something that has been taken care of by the KL regularization term. We want to make sure that our inputs are well reconstructed, and importantly, we want to make sure that when we generate, that is when we sample from Z, we obtain images or anyways samples that look real, that are believable. So good extrapolations therefore, right? One way that we can do this is by grid searching on Z. So we go around 0, 0 for instance in a 2D latent space, and we generate or we sample Z's in a grid, and then we observe what kind of generation we obtain from these Z's, and this is seen here. Specifically, this is a nice example. So I think this is a 2D latent space, right? So 1D, 2D, so 2 dimensions for our latent variables, and we observe that for we obtain the Z values here, Z1 and Z2, in a grid, and for each of these Z dots, I'm generating an MNIST type of image. And we observe that actually our generations are not too bad. So in the top left, I see something that looks like a 6, and then when I change only Z1, I keep Z2 fixed, then I start obtaining something like that looks like 2, and then something that looks like a 4, and then when I go from top right to the bottom right, I start from 4s and then go to 7s, or to 9s and then 7s. and then from the bottom right to the bottom left, I'm moving from 7s to 0s, and then where I go inwards, I start getting slanted digits. So all these are actually very reasonable. And here is another visualization of the latent space. We observe a high concentration in the middle here. This is not unreasonable at all, since I have a unit Gaussian in this example as a prior after all. So it is expected that most of our posteriors, approximate posteriors, we're going to, when aggregated, the aggregated posterior will look like the unit Gaussian. And in the top left, in the far left, we now see also generations from face images. They actually look quite nice, quite crisp on the face, however quite also blurry in the background and on the edges. This is a general observation for VAEs with various explanations given for the blurriness. One explanation is that VAEs rely too much on the Euclidean loss, so a least squares type of error, and that one penalizes outliers, and with edges you might have like sudden changes, and therefore the neural network is encouraged to have smoother transitions. Another explanation is that standard VAEs rely on too simple prior distributions like unit Gaussians, which cannot really capture the intricate patterns that one might observe in real images. In any case, the generations are actually quite good, and at the time they were impressive. Now, to train variational autoencoders, we have to maximize our evidence lower bound, and our evidence lower bound comprises two integrals. The first integral is the reconstruction term. The second integral is the KL divergence term. Normally, you have to derive the maths behind the two integrals, and it's a good exercise to try to derive the elbow for Gaussian latents and Bernoulli outputs. Often the integrals are still intractable. After all, we have latent space Z that are huge, so what we do is we typically resort to Monte Carlo averaging, which can couple well with backpropagation. So we can still use backpropagation for our neural networks, and Monte Carlo averaging to average over our latent space to marginalize out our latent space Z. So in that case, forward propagation means evaluating these two terms in isolation, well, not in isolation, but like computing these two terms, and backpropagation means computing the gradients of the elbow with respect to our parameters theta and phi. Training the reconstruction term means trying to optimize this first integral, which is an expectation and more often than not, cannot be solved analytically. So in that case, what we do is that we are using our approximate posterior as our density function here. And we sample from this Q, right? So we sample a latent code Z, and then using this latent code Z, I'm creating a generation. Then I'm measuring how much this generation looks like real data. Basically, for Gaussian variables, this looks a lot like Euclidean loss function in the end if you do all the math. But in that case, you have to make sure that your conditional likelihood couples well with the logarithm. If our estimator for estimating the sample average in this first integral is low variance, so we have a low variance estimator, in practice a single sample of Z is enough. We don't have to sample 10 or 100 times per image. Just sampling once from our approximate posterior is going to be good enough. And of course we'll have stochasticity, but in fact, this is desirable because it adds some noise to our computations, which means that the neural network cannot overfit to particular parameters. It has to maintain a generally good solution. Now, how can we get a low variance estimator? We can rely on the reparameterization trick for low variance estimation, as we'll see in the follow-up sub-lecture. In training the KL regularization term, we have another integral, and in fact, this can be a simpler term to compute. The reason is that more often than not, we have known distributions here. So we know that our prior distribution, for instance, is a Gaussian, a unit Gaussian, whereas our approximate posterior is again a Gaussian. We don't know its precise parameters, so the mu and sigma are parameters that we are, computing or optimizing. However, we know it's a Gaussian, and the fact that we're having a KL divergence between two Gaussians means that we can simplify this integral into perhaps a closed form solution, which is the case for this example. However, it can be that a closed formula solution is not possible. In that case, MC, so Monte Carlo averaging, is still possible, right? So we just sample again from our approximate posterior and do a compute, or we average over the remaining quantity.